Hi, there's a time in every practical session when things that we've done in theory don't quite match up with what we do in the practical. At least that's how things seem until we take a closer look. So today we're working with the basic power supplies laboratory using a regulator panel with a 7805 5-volt DC regulator, and we're powering it with a bridge rectifier and a small AC supply going into a 50 ohm load resistance, and we're going to measure the current and we're going to measure the voltage. And on the meter, what we get can be a little bit puzzling to start with, and that's where we need to understand a bit more about the theory. So let's go and have a look at this lab and let's see what's happening. Let's see if that theory and the practical do really match up, or whether we've got a small problem here. Okay, I'll just try and sneak my head into this scene. So we're about to get on with the show then with our 7805 3-terminal regulator panel and see if the theory for the regulator panel matches, or the practical matches the theory, I should say, what we did in class the day before. So I've got a AC power supply here, a transformer, 12 volts RMS coming into a bridge rectifier. 1.414 times that RMS voltage should give me around about 17 volts out of this panel, and then that 17 volts unregulated DC with a degree of ripple in it, no doubt, comes into the 7805 regulator, 3-terminal regulator panel. In this case, there's a switch on the panel, and when the switch is in position 1, it puts the control pin down to ground to give me the voltage of the regulator proper, 7805. I have a current meter connected to the panel, and the current meter currently is telling me that I've got 153 milliamps of current flowing into my load resistor of 20 ohms, and that's no doubt a power resistor under this panel. And the voltage that I'm getting across the output, let's just get these leads. So, oh dear, only 3 volts. What on earth is wrong here? Only 3 volts of DC voltage. DC average voltage, perhaps, depending how much ripple there is on the output of my 7805 panel. What can possibly be wrong? At this point in time, I'd have to suspect that maybe I haven't got enough input voltage to the 7805. Therefore, the 7805 is not regulating properly. Therefore, the output is lower than 5 volts. That would probably be one of the first things I would want to check. So I'll just move that DC voltmeter and we'll put it over here onto the output of the bridge rectifier panel. Oh, I can see I've got a problem here. 10.5 volts average DC voltage coming out of this panel. I'm expecting 17 volts out of this, but obviously if we're loading the circuit down too much and there was some resistance from the transformer coming into the bridge or from the bridge before the output terminals, maybe that's why the output's loaded down. But really I can't see enough with just the digital multimeter. So this is at the point where I think I need to now reach across and plug in the oscilloscope to find out what's happening here. So we plug the oscilloscope in, and time now to hook the oscilloscope up to the circuit perhaps. Let's put that voltmeter back on the output of the circuit. 3 volts, and come across here to the input, and I'm seeing a stack of noise happening there. What on earth is this that I'm getting? Here in Australia we use 50 Hertz for the main supply, so the period of one full cycle of 50 Hertz is 20 milliseconds, so therefore each half cycle is 10 milliseconds. I should have 10 millisecond pulses of ripple that I'm seeing here, but I'm seeing a whole lot of wretched noise. Why am I seeing that? One reason could be, do you remember this capacitor at the input of the 7805? This has to be added to the 7805 and all 3 terminal regulators, in fact, where the input of the regulator is more than about 6 inches or 150 millimeters away from the reservoir capacitor following the bridge rectifier. I could have a quick look underneath the panel, I guess, and see if in fact I've still got that connected up. Oh, look at this. We've got even noise just I'm picking up by putting the probe near it, so we've certainly got some oscillation taking place. Why have we got all that oscillation taking place? We have a quick look underneath the panel, and I can see here I've got the small capacitor C1. It's still connected, there's nothing wrong with the leads, so it's not a case that the capacitor is disconnected from circuit. But we have this major problem. We've got oscillation taking place, we've got the output voltage down quite low. Again, if I move the oscilloscope across and have a look at the output, I'm guessing I'm going to see some pretty weird things happening here too. We've got things dancing around all over the screen on the oscilloscope. See, you cannot see this with the DVM, the digital voltmeter, but I can see this happening here quite clearly with the oscilloscope. And look at this weird ringing and oscillation that I've got happening here. Well, look, and I mean, you know, we're pretty certain that the oscillation's coming from this, so we'll prove this in fact by disconnecting the mains from our power supply. I've unplugged the mains. We've got no power happening in the circuit. All the oscillations disappeared. Yes, in fact, then that's what we had happening. We do have something happening in our circuit causing oscillation. What can it be? Well, the fact that we measured before only 10 volts of DC, 10 volts DC average voltage across the output of this board, now I'm starting to think that perhaps the filter capacitor is not connected. And we look there, we've got a 1000 microfarad, a 2000 microfarad filter capacitor. Oh dear, look at this. We have a switch unfiltered in the middle position. So unfiltered, we're just going to have the full ripple voltage of 17 volts peak to peak. Alright, first of all, let's put in a capacitor and let's see what happens with the output voltage, just to confirm our diagnosis. 4.6 volts DC, it's certainly jumped up dramatically. How hot is our regulator? Underneath the panel there is a heatsink connected to the 3-terminal regulator, and the 3-terminal regulator is moderately warm. We had 180 milliamps, I think it was, of DC current before, average. Now I've gone to overload condition on the 200 milliamp scale, so I've got a much smoother DC voltage coming into my regulator board at the moment. The 4.61 volts, I do have the output heavily loaded with a 20 ohm resistor. We'll go up to a 50 ohm resistor, so we're not drawing so much current from the board. And now we're at 100 milliamps, let's call it 98 milliamps. So 20 ohms, I would have been probably 220 milliamps, something like that. So that's why it was overload on the range. Alright, let's, now that we haven't got oscillation happening, let's move the oscilloscope back to the output of the bridge rectifier panel, and let's have a look at what the ripple is at that point at the moment. Okay. Hundred millivolts per division, 200 millivolts per division. Alright, here we go. There's still a bit of noise on that, but try and get that to synchronize there. Always check the triggering on the oscilloscope. Menu, source, channel 1. That's exactly where we want it. 500 millivolts per division, position control. 1.5 divisions, 1.2 divisions, 500 millivolts, about say 600 or 700 millivolts of ripple happening there. So the capacitor is not quite big enough to maintain a charge, even with 50 ohms load and only 100 milliamps of current in the load. 100 microfarad is not quite big enough to act as a reservoir and get rid of that ripple. So 500 millivolts, yeah, 600 millivolts peak to peak ripple. There's of course with unfiltered, that's horrible. We're back to our 3.53 volts. 2000 microfarads of reservoir capacitor now, and we've come down not 500 millivolts ripple, but we're down to about 350 millivolts peak to peak ripple. That's looking much, much nicer. What I'll do now, I'll disconnect my load panel off here, and we'll plug the load panel directly into the bridge rectifier. And I'll go for unfiltered, and 5 volts per division. I'm on AC coupling. I should probably do this on DC coupling, but not to worry. 5, so we've got 17 volts peak to peak, and that's exactly what we'd expect to have. We're on 5 millivolts per division, and sorry, we're on 5 volts per division. We're on 5 milliseconds per division. And we just want to move that along, and 1, 2, 3, 4, 5, 10 milliseconds, exactly what we expect to get with 1 half cycle. Because don't forget, bridge rectifier, 2 diodes are acting for 1 positive half cycle, 2 diodes are acting for 1 negative half cycle, and bringing it back up to the top. So if we had a half wave rectifier panel, we'd see a big gap missing in between these half cycles. So full wave rectification, that's what we see, and that is the ripple voltage is going to be equal to the peak to peak, or the peak output voltage of that bridge rectifier. So 2000 microfarad, that's what's happened to the ripple. It's got rid of a lot of it. 1000 microfarad, still got rid of a lot of it. We can see that we've got an average voltage there. We've got the ripple floating around 10 volts. It is dropping below 10 volts. Look, I might just go to DC coupling on this. I'll just get that off there because I don't like to do measurements on channel 1, AC coupling, DC coupling. If we're going to do proper measurements, we want to have DC coupling with a baseline measurement there. There's 0 volts baseline. We'll plug that back in again, and that's more like it, because now we haven't got the effect of the input capacitor of the oscilloscope. So before I could certainly read the peak to peak like value of ripple, but it was very awkward to read the average value of DC. So now I could take an average straight through the middle of that for my DC. 2 volts per division, 2, 4, 6, 8, 10, 12, 14, the middle line through there. So we've got about 13 volts average through the center of that with the 1000 microfarad. There's the full ripple voltage with no capacitor coming in, and with the 2000 microfarad capacitor, again the ripple is much smaller, so the average output voltage is higher. Now the problem is with ripple, with a regulator circuit or a Zener diode circuit, the ripple voltage can drop down below the headroom that's required in a regulator, or below the knee current in a diode regulator circuit, and stop regulation. So ripple coming into any type of regulator circuit is a big problem in the trade. If capacitors dry out and we start to get too much ripple, we start to get dropout and we don't get the right output voltage. There's another switch on this board. Switch 1 uses it as a 5 volt regulator. Switch 2 adds a 150 ohm and a 220 ohm resistor, which will have the effect of lifting the control pin on the 7805 and giving me a higher output voltage. So I'm just going to rewire this quickly and put it back to, oh, the smell of warm resistance. It wasn't burning, but it was getting a little bit on the hot side. We'll give that resistor a bit of a rest and we'll go to the 50 ohm resistor here. I'll put the voltage meter back in across that 50 ohm meter. We'll leave the 2000 microfarad capacitor hooked up. Turn that meter back on because he's decided to turn himself off. And we've got about 9 volts, very close to 9 volts on the output. Remember, that was with the control pin connected. Position 1 puts a short circuit across the 150 ohm resistor. We're down to 5 volts. Let's call it 5 volts, 4.8 volts. If I take the load off completely, we'll jump up to 4.97, 5 volts. 50 ohm load, we've got 4.8. 20 ohm load, we'll probably drop down to about 4.6 volts. I go to position 2, lift the control pin voltage, and with a very light load, I was just under 9 volts. I think I was 8.98, and with no load, I'm up to 9.15 volts. Let's go back to that 50 ohm resistance. That'll be 8.8 volts. All right, so the maths for this, we have to divide one resistor into the other, and we have to multiply it by a standard, and that'll come up with the, that'll allow us to see what the derived voltage will be at the output. Now, as a tail end of this video, I'll do the maths on that, and we'll just confirm that we have got the ratio of those resistors with the 7805 set for 9 volts. And also I might just add here, if we're using an LM317, the control pin has a lot less current going down through it, which allows us to use things like 2.2K, 5K variable resistor to make it a fully variable output supply. To make this variable, I'd need a wire wound resistor because I've got too much current coming down through the control pin to work with a standard carbon resistor. And that pretty well wraps up what we were trying to achieve today with our 7805. Oh, maybe one more little thing, and it just comes to mind because the current meter has decided to drop out on us there. Let's get rid of the voltage meter across the output and let's see what's happened to the ripple after the regulator, because a lot of these regulators have got like about 40 or 50 dB of ripple rejection. And there we've got a 50 ohm load resistance. There we've got, we're on DC coupling, 2, 4, 6, 8, tad over 9 volts. And if we want to, can't see any ripple there, if we want to see the ripple, we probably need to go back to AC coupling and just lift our position up a little bit and really boost things up here. I'm down to 10 millivolts per division and I can't see any ripple. There's absolutely no ripple across that load at all. But if I go to the input of my regulator board, I'm glad I remembered to do this because I don't script these videos. If I go to the input of my regulator board and I look at the ripple, oh, we're back to a bit of noise because I've added things here. We've got a bit of noise happening. Here we go. We got lots of ripple happening. And because of that noise on there, and what you can do, I'll show you something. Trigger, menu, setup, coupling DC. You want to go to HF reject, because when you got a circuit like this, which has got a whole lot of high frequency oscillation that might occur with it, the only way you can probably synchronize this properly is to get rid of that HF with a filter built into the oscilloscope. So we know that we're sitting on 9 volts, 9.1 volts, something like that. So we don't need DC coupling to see the DC level. I'm only interested here in the ripple. So 200 millivolts, 1, 2, 3, 600 millivolts peak to peak of ripple. Whereas on the output of the regulator, I had no discernible ripple at all. We'll just go back. It'll be the last thing we'll do, and that'll be the end of this video, other than those calculations that I promised to do. So there we are, 10 millivolts per division, a little bit of noise there, absolutely no ripple at all. So these have a lot of ripple rejection, absolutely beautiful. Even if we go down to 1000 microfarad, still no ripple, compared to oh, look at all that lovely noise, compared to a stack of ripple there. Oh, with 1000 microfarads, we've got 500 millivolts, we've got 1.3 volts peak to peak, 1.3 volts peak to peak of ripple with 1000 microfarads, and about 1 volt peak to peak ripple with a 2000 microfarads. And with either capacitor, we had no discernible ripple happening across the output. All right, this has been Greg Moore for TAFE New South Wales, stretching the neck to do the 7805 3-terminal regulator lab overview. Don't forget to stay on the video to see the calculations for the 2 resistors to step up the control pin on the IC. Thank you. Okay, well, we finished the lab, and like I said, we'll come back to the board now and we'll have a look at the circuit for the 7805 3-terminal regulator with adjustable 2 resistors added to that circuit to lift the output voltage just that little bit. So, I've drawn the circuit up here on the board. Here's the 7805 regulator, 3-terminal. Here's our control element down through here. When that switch was in position 1 in the lab, we had the control element going straight to ground, so we got the terminal voltage of the regulator at the output, which was 5 volts or maybe 4.8, or under extreme load, maybe down to about 4.6. That's to be expected. Other things in this circuit that we need to look at, we saw before, to prevent oscillation, this critter here, this first capacitor. We if that capacitor is not in the circuit and you're more than about 6 inches or 150 millimeters away from the unregulated input to the 3-terminal regulator, you might get some oscillations, and we in fact saw some of those oscillations occurring in our circuit. Even though we had that capacitor, we had some horrible things happening with no filtering over here coming out of our bridge rectifier earlier on. I've drawn a bit of a resistor here, and this is to show what happens with this diode at the top. This is a protection diode at the top of our circuit. And if the input was to go short circuit for some reason, maybe a spike takes out 2 of the diodes in the bridge rectifier, and then we've got nothing coming in the way of voltage into our 7805, but we do have a charge in this capacitor. That charge then can come back up through this diode and back and flow down through here to ground safely. If we did not have that diode in the circuit, any charge on that capacitor, or indeed any other downstream voltage that can come back into here, could come into the output of the 7805 or any 3-terminal regulator and damage it, and we don't want that to happen. Anyway, what we're going to talk about now is these 2 resistors, R2 and R1, and we have to apply an equation to that to find out what the output was in our circuit. And that's going to be, in this case, equals the nominal terminal voltage of the regulator plus R2 outside of the nominal terminal voltage divided by R1 added to the quiescent current, I0. And that quiescent current in this case is going to be around about 2.5 milliamps. That's pretty standard for one of these critters coming down through there. The LM317 is going to have a lower quiescent current. It's been designed to run with higher values of resistors in the control leg. If we put some values into that, then we're going to have 5 volts added to 150 ohms outside of 5 volts over 220 ohms added to 2.5 milliamps. And in fact, this is going to give us a current anyway, a voltage over a resistance, very low current. And after we run the maths on that, we come up with, I think I worked out 8.8 volts, something around about there, 8.78 volts, I think, from memory when I did the sums. I didn't write the answer down on my paperwork. 8.78 volts. On the day, we flicked the switch, we put these two resistances into our circuit, and in fact we got, from memory, 8.6 volts with a 20 ohm load that was severely loaded, 8.8 volts with a 50 ohm load, and we got about 9.2 volts with no load on the output. So that's not bad, and if you do need to change that a bit, you can always put small resistor, or a large resistor I should say, in parallel with R2 to decrease its value a little tiny bit, or you could even put another series resistor in one of the legs of that resistor, and you could up its value a bit to make the output voltage a little bit higher. So if it's really critical, we want to use a 7805 or a 7808, 7809, 7812, something like that, and we want to lift the output voltage, that's the way we do it. We use these two resistors like that, and you can always fine-tune the value of the R2 resistor. All right, so that's what I said. It's a conclusion at the end of the lab. The video for the lab ran a little bit longer than I wanted it to. I should have talked faster maybe. But anyway, that wraps it up. And I think on the day, all of the theory that we've done with our ripple voltage and 3-terminal regulator and reservoir capacitor all stacked up for us with that lab. So this has been Greg Moore for New South Wales TAFE, teaching 3-terminal regulators in practice. Thank you.